Yes.
Yeah, here today we're going to start transient behavior and initial conditions. Okay, that is simply we call it as transient analysis. Okay, actually, why we needed this transient analysis? Because if my network contains any kind of energy storage element, okay, what are the energy storage elements? Inductor, capacitors. If my network contains this type of energy storage elements, then they are going to switch it from one condition to another condition. It means whenever I am going to apply some kind of energy, or if one circuit is there here with inductor and capacitor, okay, here these initial conditions initial conditions are not known to us. So this is a these two are L and C are the energy storage, where what I'm going to do, just I'm going to apply a source here, one source plus minus. Then the condition of this condition in the sense in terms of voltage and current, the conditions of this inductor and capacitor will change. Okay, how they are going to change instantaneously or linearly, that will see in the next section, where okay, the time taken to change from, see here, the time taken to change from an initial condition an initial condition or initial steady state initial steady state to its final steady state final steady state. Okay, we are going to call this one as a transient period. What do you mean by transient period? The time taken to change from initial steady state to its final steady state. This is my transient period. Okay, now to this transient friends, I am going to plot some responses. That one I am going to call it as a transient response. Okay, where the response of the network after it attains a final steady state value is independent of the time. Is called the steady state. See, steady state in the sense what? The value here, the value of this final steady state is independent in independent of time. Okay, that is a steady state response. The complete response of the network is determined with the help of differential equations. Here in transient analysis studies, what we are going to do? We are defining some differential equations. Okay, first we are going to make some initial conditions. We are assuming some at what time of t we are going to insert this source, or if I am having any switch here in between, okay, at what time I am going to close this one. Depend upon that, we are going to write some differential equations. Then we will see how the inductor, capacitor, resistance will behave. Okay, first of all, initial condition here, initial conditions. Okay, the name only says initial conditions. It means in solving the differential equation in the network, we get some arbitrary constant. That is nothing but initial conditions are used to determine these arbitrary constants. Okay, where what I'm going to do? See here. the differentiate between the time immediately before and immediately after switching. See, immediately before that I need to draw one circuit. Okay. Okay, here some resistance, inductance, capacitance, some source. Okay, this is a switch R, L, C. Okay, now I want to know the behavior of these elements: resistance, inductance, capacitance at the time of switching. Okay, now what I'm going to do, I'm going to differentiate before, see, immediately before and immediately after. It means this switch is closed at, we are going to assume switch is going to close at t equal to 0 second. Okay, now I am going to assign some signs. The sign immediately before we are going to assign with a negative sign. Okay, the sign with immediately after closing the switch, I am talking about this switch. Okay, immediately before the closing switch will be assigned with a negative sign. Immediately after closing the switch, I am going to assign with a positive sign. Okay, the condition existing just before switching are, see, conditions, initial conditions just before switching, just before switching are I and V. First I O minus and V O minus. Okay, then just after switching, conditions just after switching are I 0 plus V 0 plus. Okay, these are the conditions just before switching and just after switching. Okay, we are going to denote it I0 V0 minus minus for just before, plus plus after switching, just after the switching. Okay, sometimes what will happen, we are going to evaluate the constants at t equal to infinity also. These are known as, this t equal to infinity are known as final conditions. Okay, this is what the basic behind this. Now what I'm going to do, I'm just summarize. Okay, in solving the problems for initial conditions in the network, we are going to divide the time period, that t, we are going to divide in three. Okay, three ways. First one, just before switching, just before switching, that is from t equal to minus infinity to t equal to 0 minus. We are going to divide the time period in three different types. First one, just before switching, that is from t equal to minus infinity to t equals to 0 minus. Okay, now second one, just after switching, just after switching, where at t equal to 0 plus. Then third one and final, that is after switching, that is for t is greater than 0. We can add to this that the final steady state at t infinity. Okay, now when you are going to say that our network is in the steady state condition, if the network remains in one condition for a long time, we are going to call it as a steady state condition. The network is under steady state condition. Okay, first, initial condition for resistor. Just remember this, just before switching, minus infinity to 0 minus, just after switching, t equals to 0 plus, then after switching, t is greater than 0, and for the final steady state conditions, t equals to infinity. Okay, now we will see how resistor will behave. Initial condition for resistor. Initial condition for the resistor. Okay, now see here, if this is my resistor R, okay, if I am going to apply any source to this, see, I am going to apply one source here, that is V of t. Due to this source, the circuit is closed, the current will flow, that is I of t. Okay, now the resistor, how it will behave before and after connecting this voltage source. We are going to relate this current and voltage source by, tell me, what is the Ohm's law? Just tell me correct voltage in terms of current. Yes, anyone?
V is equal to IR.
V of t is equals to R into I of t. Okay, where the current through resistor will change instantaneously. It means whenever I am going to apply this is a voltage source V of t to the network containing a resistor, the current will change instantaneously. It means whenever I am going to change the magnitude of my voltage source, the current will also change. Okay, so the resistance, the current through the resistor will change instantaneously if the voltage changes instantaneously. Similarly, the voltage will change instantaneously if the current changes instantaneously. It means current flowing through resistor will change according with the Vt. Okay, or if I am going to connect a current source, the voltage across the resistance will change instantaneously when the current through the resistance will change. Okay, this is about the resistance. It means, see here, now initial condition for inductor. Okay, now tell me, if I am going to replace this one inductor, okay, fine. Now tell me, what is the voltage if I'm going to replace this one with this L, voltage V of t, I of t. Tell me V of t. V of t is equals to L di by dt. Correct? Where the voltage across the inductor is proportional to the rate of change of the current flowing through the inductor. Okay, it means what? We cannot change the current through inductor in a finite zero time. It means instantaneously the current will not increase according to the applied voltage. Okay, this requires some infinite voltage across the inductor. So an inductor does not allow an change in the current through it. Okay, now current through inductor is given by I of t is equals to 1 by L 0 to t Vt dt plus I of 0. See here, this I of 0, see where I of 0 is the initial current through the inductor. It means before connecting the voltage